Hello guys, I am Vaishali Kikan and we are discussing chemistry. So moving on towards the next chapter, which is the acids and bases, we are going to discuss some of the concepts and some of the numerical problems so as to understand this chapter in detail. So let's start our discussion with the properties of the acids and bases. First of all, we are going to discuss the various properties of the acids and bases to understand acids and bases in detail. So with the help of this table, we are going to understand the properties of acid and bases. The first property is the pH. The pH of acid is lesser than 7, whereas the pH of bases will be greater than 7. The next property by which we are going to understand the acid and bases is the electrical conductivity. The electrical conductivity of acid will vary, whereas if I talk about the base, the electrical conductivity of the base will also vary. So both acid and base will have the variable electrical conductivity. Now the next property is taste. Although you are requested not to taste the various chemicals, so never do this in lab, right? So if I talk about taste, so acid will be having sour taste, whereas base will be having a bitter taste. Now coming to the next property, which is feel. Again, you are not requested to touch the corrosive chemicals, whereas we have written the corrosive word on the chemical, don't touch those chemicals. And if I talk about the feel, acid will not be having any kind of special feel, whereas base will be having a slippery feel. Why we have the slippery feeling for base, that also I am going to tell you in this particular video itself. Now coming to the next property, which is a color change with acid base indicator. We have some indicators which change color if I put the acid into it and if I put the base into it. So based upon the acid or base, the indicator is going to change the color, right? So first of all, the first indicator is bromothiol blue. If I put the bromothiol blue in acid, it will turn yellow. In base, it will turn blue. Coming to the phenolphthalein. Phenolphthalein is again an acid base indicator which turns the colorless. It turns into colorless when acid is put into it, and when base is put into it, it remains purple. Original color of the phenolphthalein was also purple. Now coming to the methyl orange. It has the red color with acid and yellow color with the base. The next type of acid base indicator is the litmus paper. So litmus will be turning red with the acid and blue with the base. So any of these acid base indicator will be used to indicate whether this solution is an acid or it's a base. Coming to the neutralization reaction. So the neutralization reaction is a reaction where the acid neutralizes base or the base neutralizes acid. So in both of the cases, in the acids as well as in base, the neutralization reaction will occur, and we are going to talk about it also in detail. Coming to the reaction of acids. So whenever I have acid and when I put metals into acid, so metal plus acid is going to release the hydrogen gas. For example, magnesium in the solid state plus 2HCl, hydrochloric acid in the aqueous state, gives MgCl2 in the aqueous state plus H2 gas. So this hydrogen gas is released when magnesium is placed in hydrochloric acid. Now coming to the carbonate compound. Whenever we have the carbonate compound and we are placing acid onto them, we will be having the release of the carbon dioxide gas. For example, we have the calcium carbonate CaCO3 in the solid. It is reacted with acid 2HCl. Hydrochloric acid is reacted with it. So CaCO3 in solid plus 2HCl aqueous gives CaCl2 in aqueous plus CO2 gas. Here you can see carbon dioxide gas is released plus H2O in liquid. Now coming to the reactions of bases. What are the various reactions of the bases? Base plus carbon dioxide will give the carbonate. So let's understand this with the help of an example. We have a base CaOH2 in aqueous plus, if I add carbon dioxide to it, I told you it is going to form the carbonate. So CaOH2 plus aqueous, CaOH2 in aqueous plus CO2 in gaseous form gives CaCO3 in solid plus H2O in the liquid. So here we have formed the calcium carbonate from the base. So the next reaction of the base is the base plus oil or fat gives soap. This reaction is also known as soapinification, where we have the base reaction with oil or the fat to form a soap. So now this also explains why we have the slippery feeling when we touch the base. We know on our body we have various oils on our skin, right? So these oils are going to get in contact with the base when you touch the base. So oil plus base is going to form soap, and this soap will give you a slippery feeling. So slippery feeling because oil is present in the skin, which reacts with the base when you touch the base, and it is going to give you soap mixture. Now coming to the naming of acids and bases, we have the various criteria of the naming of acid and bases. We are going to understand this with the help of this chart. So in the 16th century, we had a highly corrosive mixture which was named as muriatic acid. So this muriatic acid, actually it is the hydrochloric acid which was named previously as muriatic acid. Similarly, previously the caustic soda was named for the sodium hydroxide. So sodium hydroxide previously was called as a caustic soda, right? So now coming to the naming, if I have acid which is having Ha structure, so we have a hydrogen which represents H, and we have an A which represents the rest of the anion right over here. So then we have the aqueous. Why? Because whenever we are forming an acid, we are putting the acid in the water to form the ions which are dissolved in water. So acid will always be formed by dissolving in the water. So acid without oxygen will be remaining with the prefix hydro and the suffix ic acid. For example, HCl is represented as hydrochloric acid. So here we have the prefix hydro and suffix ic acid. Similarly, Hi is represented as hydroiodic acid, right? So now coming to the naming of the acids with oxygen. Without oxygen we know hydro-oic acid, right? Then we have the acid with oxygen. We have the acid with oxygen which have the oxyanion. Whenever we have oxygen, we have the oxyanion in the acid, right? Acid plus oxygen will always have an oxyanion. Now we have the oxy acids, and based upon these oxy acid, in the oxyanion we have the anion, and this anion will be forming an oxy acid. This oxy acid will not be having a hydro prefix. Hydro prefix is used to represent that only hydrogen ion is present, right? And we have the acid in the form of Ha, right? So oxy acid will not be having the hydro prefix. So when I have the different types of oxyanion, we have the different types of naming. For example, we have the oxyanion which is ending. So if the anion is ending with the 8, the acid name will end with ic acid, right? For example, if I have the anion NO3 negative, which is the nitrate ion, so it is ending with 8, so the acid will be HNO3, which is the nitric acid, which is ending with ic acid, right? So now if I have the oxyanion ending in ite, so whenever I have the oxyanion ending with ite, so acid name will end in OS acid. For example, if I have the ion NO2 negative, which is the nitrite ion, so here we are ending this ion with ite ion, right? So the acid will be HNO2, which is the nitrous acid, right? So here the acid will end with OS acid, nitrous acid. Similarly, we have different names. Nitric acid, HNO3 aqueous. So here we have the nitrate NO3 negative parent oxyanion. So acid is nitric acid, which is represented as HNO3. So the parent oxyanion is NO3 negative, which is nitrate. So 8-ic acid. Similarly, here we have chlorate. Chlorate is the parent oxyanion, which is ClO3 negative. So its acid would be chloric acid at ClO3. Similarly, we have carbonate. So here we have the parent parent anion, which is 8. So CO3 2 negative will be forming the carbonic acid, H2CO3 aqueous, right? So whenever we have the ion carbonate CO3 2 negative, it is forming the carbonic acid H2CO3 aqueous. Now moving on to the sulfuric acid. Sulfuric acid will be having the parent oxyanion as sulfate, which is SO4 2 negative. SO4 2 negative is ending with 8. So here we will be having the name of the acid to be sulfuric acid. Now coming to the next oxyanion, which is phosphate. So again it is ending with 8, so the acid will be having the suffix ic acid. So phosphate is PO4 3 negative, it will be having acid H3PO4, which is phosphoric acid. Right, so I hope you understood the basic naming. Now coming to the chart where we are studying how to name the acid. So does the formula of the acid include oxygen? This must be our first question. If the formula of the acid is not involving any oxygen, we have the name of the acid is in the form hydro-ic acid, for example hydrochloric acid. Now coming to the next case where we have the formula of acid which is including oxygen, it is an oxy acid. Whenever the acid is oxy acid, we have to see what kind of ion we have, right? So first when we have the ion which is in the form of per-8 ion, right, where we have one more oxygen than the required oxygen, right? So one more oxygen than the parent oxyanion, which is represented as per-8 ion, right? So its acid is per-ic acid, for example perchloric acid, right? So we have to see how many oxygen are present in the ion, right? So if I have more oxygen than the parent oxyanion, then per-8 ion, one more oxygen only. Now if I have only the parent oxyanion, which is represented as -8 ion, so at that time we are going to represent this acid as -ic acid, like chloric acid is the example. Now coming to the next case, when we have one less oxygen in the ion, like we have to represent this ion as -8 ion. So here we are going to represent the forming acid as -OS acid, and the example is chlorous acid. The next case is when we have the fewer oxygen in the oxyanion, so it is represented as hypo-ite anion. The anion is represented as hypo-ite anion, so the formed acid is represented as hypo-OS acid. So the example is hypochlorous acid. Based upon this, we have a question which states write the name of the acid with formula H2SO3 aqueous. So now here if I see this structure of this acid, so if you see the formula, we have the oxygen in the formula. So when the oxygen is present, we are not moving to this naming culture, we are now in this naming culture. So oxygen is present, and which means we have an oxy acid. Oxy acid is related to the oxyanion. Now which is the oxyanion over here? SO3 negative. SO3 negative is my anion, which is sulfite anion, right? So sulfite anion will be having one less oxygen. Actually the anion, the parent oxyanion is SO4 2 negative, right? We have one less oxygen, so it is represented as sulfite anion, right? So sulfite anion will be forming the sulfurous acid. Sulfurous acid, because here we have the ending with OUS, right? So I hope you understood this. Now coming to the Arrhenius theory of acids and bases. Arrhenius theory of acids and bases were given in 1880 by a scientist which was a Swedish chemist, and its name was Svante Arrhenius. So what was the theory all about? The theory was all about the electrolytes. So he told that the electrolyte, for example, we have the sodium chloride electrolyte. So electrolyte will conduct electricity, right? So this theory told that why the electrolytes are going to conduct electricity. The electrolyte will be getting dissolved, and when they are going to get dissolved, the ion dissociates, which means the ions are going to come apart and they move freely in the solution. When the ions are going to move freely in the solution, that time they are going to conduct the electricity. In 1880s only, Arrhenius now modified this theory. Arrhenius modified theory, and this modified theory will include acids and bases also, and this modified theory told that the acids and bases will also contain ions, and thus the acids and bases will also conduct electricity. Now we are going to understand the acid and base when they are going to get dissolved in water. So base is going to form cation plus hydroxide ion, right? So hydroxide ion is OH negative. For example, we have CaOH2 in solid, it is going to give Ca2 positive aqueous plus 2OH negative aqueous. Now when I have the acid is going to produce the hydrogen ion For example, we have HNO3 aqueous, it is going to form H positive aqueous plus NO3 negative aqueous. So we have acid and base reactions that are going to produce hydroxide ion and the hydrogen ions. Now coming to the dissociation. What is dissociation and how it is different from ionization? Dissociation is the process where water molecules pulls positive and negative ions of the ionic hydroxide. Right, so when I have the ionic compound water, we know water molecule is polar, and the polar water molecule is going to attract the positive and negative ions of the ionic hydroxide. In the ionization, we have the formation of ion from uncharged molecules. So how we are going to represent the dissociation? In the dissociation, we have the ionic compound M positive X negative in solid gives M positive aqueous plus X negative aqueous. So water is going to surround them. Now coming to the ionization. In ionization, we have Ha aqueous. So here we are not having the ionic compound, right? So it is going to form H plus aqueous plus A negative aqueous. Now coming to the neutralization reaction. In the neutralization reaction, we are going to understand the neutralization reaction by the reaction of hydrochloric acid with sodium hydroxide. So hydrochloric acid, we know it is going to dissociate in water. So when you are going to put the hydrochloric in water, so HCl in aqueous gives H positive aqueous plus Cl negative aqueous. So this is a reaction for HCl aqueous. For the dissociation, similarly we have NaOH aqueous, it is going to form Na positive aqueous plus OH negative aqueous. So when we are going to mix them, both of them, then we are going to have the total ionic equation. In the total ionic equation, what we are going to do, we are going to add these two equations, right? So what we have, H positive aqueous plus Cl negative aqueous plus Na positive aqueous plus OH negative aqueous gives H2O in liquid plus Na positive aqueous plus Cl negative aqueous. So now in the total ionic equation, you can see we have added the ions of both of the reaction and we have formed the water H2O liquid plus Na positive aqueous ion plus Cl negative aqueous ion, right? So here you can see we have the Na positive and Cl negative as the spectator ion which are going to get cancelled out, right? So when we remove the spectator ions, what is the actual equation? We are left with H positive aqueous plus OH negative aqueous gives H2O in liquid. So this is the reaction that we are left out with. So now coming to the simplified neutralization reaction. The simplified neutralization reaction is simply H positive aqueous plus OH negative aqueous gives H2O in liquid. So now coming to the concept which is a strong and the weak acid. What is a strong acid? Strong acid is a substance that ionizes completely in water and it have strong acidic properties, right? So it is going to have the low pH, it is having the vigorous reactivity. Whatever reaction we are going to talk about, this reaction will be very vigorous in the case of strong acid. The pH is very less, right, for the strong acid, and the ions are going to dissociate completely. If I have the, let's suppose if I have 3 HCl ions, all of the 3 HCl ions are going to dissociate 3 H positive ions and 3 Cl negative ions, right, in the case of strong acid. So now coming to the weak acid. Weak acid are substances that only partially ionizes in water and have weak acidic properties. So the acidic properties are weak, like they have the moderate pH and they have the mild reactivity. They have just the 2% ionization. So let's suppose if I have 100 HC2H3O2 molecules, so it is going to form only 2 H positive ions. So this is how I can say these are the non-conductors of electricity. They do not conduct electricity. Similarly, I can say ethanoic acid is a weak electrolyte which does not conduct electricity because we are forming very less amount of ions and ions are required to conduct the electricity. So this is a reaction where we have the partial ionization and it forms a weak acid at C2H3O2. So here we are going to have the partial ionization which forms H positive aqueous plus C2H3O2 negative aqueous, right? So now coming to the questions, we have 2 sample problems. So first sample problem is based upon the titration which states several 10 ml samples of sulfuric acid solution of unknown concentration are titrated with 0.1 mole per liter solution of sodium hydroxide. In the burette, we have the sodium hydroxide solution. The end point was identified with the phenolphthalein indicator. Observations are in the given table. This is the table that we have. Use this data to determine the amount and the concentration of acid solution. We have to find out the amount and the concentration of H2SO4, right? So we have the readings, final burette reading in ml, which is 12.52. In the second case it is 24.98, in the third case it is 37.62. Initial burette volume reading was also given in ml, which is 0.10, 12.52 and 25.10. Volume of base titrant added, it is also given in ml, which is 12.42, 12.46, 12.52. So first of all, I am going to find out the average volume of the titrant used. Average volume of the titrant. So what is the titrant? NaOH. NaOH was present in the burette, so it was the titrant. Whatever solution we have present in the burette, that is my titrant. So average volume of NaOH we can find out by averaging these three values. So 12.42 ml plus 12.46 ml plus 12.52 ml divided by 3, you can calculate it and it will come out to be equal to 12.4667 ml. So this is the average volume of the titrant used. Now we can find out the volume of NaOH in liter. So this is the volume that we have in the ml. We can convert it into liter by multiplying with the conversion factor 1 liter by 1000 ml. 12.47 ml multiplied with 1 liter by 1000 ml gives 0.01247 liter. Now we have found out the volume of NaOH in liter. Now volume of H2SO4 in liter also we can find out. So we have the 10 ml sample of sulfuric acid. It was also given in ml. So we can convert it into liter by again multiplying with the conversion factor 1 liter by 1000 ml. So we get 0.0100 liter. Right? So now coming to the reaction, what is happening in the given reaction? We have NaOH plus H2SO4. So NaOH will be having the coefficient 2. 2 NaOH aqueous plus H2SO4 aqueous gives 2 H2O plus Na2SO4 aqueous. So we are now focused about H2SO4 and NaOH, right? For NaOH we have calculated the volume 0.01247 liter. For H2SO4 also we have the volume which was given, which is 0.0100 liter, right? So now here we are given with the concentration of NaOH also. So the concentration of NaOH was 0.1 mole per liter, right? So it is represented as 0.100 mole per liter. Concentration of H2SO4 we have to find out. We know the formula of concentration, which is the number of moles upon volume. So if I rearrange it, so the number of moles of NaOH can be found out as the concentration multiplied with the volume. I know the concentration, I know the volume for NaOH. So the concentration into volume would be 0.100 mole per liter multiplied with 0.01247 liter, which is 1.247 into 10 raised to power minus 3 mole. This is my number of moles for at NaOH. Now I can find out the number of moles of H2SO4 with the help of this equation and with the help of various coefficients. So 1.247 into 10 raised to power minus 3 mole of NaOH multiplied with 1 mole of H2SO4 divided by 2 moles of NaOH. So here we have the coefficient 1, here we have the coefficient 2 multiplied with 1 by 2. So here we will be getting 6.233 into 10 raised to power minus 4 mole. So we have found out the number of moles of H2SO4. Now I know the number of moles of H2SO4. I know the volume of H2SO4. I can calculate the concentration of H2SO4 as number of moles of H2SO4 divided by the volume of H2SO4. Number of moles of H2SO4 we had calculated 6.233 into 10 raised to power minus 4 moles. Volume we have calculated 1 into 10 raised to power minus 2. It was given in the question. So when we divide them, I will get 6.233 into 10 raised to power minus 2 mole per liter. This is the concentration of H2SO4. Now coming to the next question, which states a 0.306 gram mass of KHP is dissolved in 50 ml of water. So now the solution is titrated with NaOH. Right, NaOH is of unknown concentration. 14.8 ml of NaOH is now used to titrate KHP to endpoint at which phenolphthalein indicator change color. Right, so I know how much amount of NaOH was used in volume. Calculate the amount of concentration of NaOH solution. We have to find out the concentration of NaOH. So volume of NaOH is given. Volume of NaOH is 14.8 ml. We can convert this into the liter. So 14.80 ml into 1 liter by 1000 ml gives 0.01480 liter. Now coming to the reaction. In the reaction KHP, which is an acid, it is going to react with NaOH to form H2O plus NaKP, right? So NaKP is the salt. These two are the acid and bases reacting to form H2O. So here the various parameters are given. The mass of KHP is given, which is 0.306 gram. Right, its formula is given, and from the formula we know the molar mass of potassium, hydrogen, carbon, hydrogen and oxygen. So with the help of molar masses we can find out the molecular mass. We know the number of moles, right, is equal to the given mass upon molar mass. Given mass is 0.306, molar mass we have calculated. So 0.306 upon the molecular mass is the number of moles of KHP, and in the simple manner we can find out the number of moles of KHP. For NaOH we know what is the volume of the NaOH used. So number of moles of KHP will be equal to given mass, which is 0.306 gram, upon the molecular mass, which is 204.23 gram per mole, which we can calculate easily, and when we divide it we can find out the number of moles of KHP, which is 1.4983 into 10 raised to power minus 3 moles. So from the equation you can see the number of moles of the KHP will be equal to the number of moles of NaOH, because both of them have the coefficient 1 and the conversion factor would be 1 by 1 for finding out the number of moles of NaOH. So the number of moles of NaOH will also be equal to 1.4983 into 10 raised to power minus 3 moles. Now I know the number of moles of NaOH. The volume of the NaOH used was already given, so I can find out the concentration of NaOH as the number of moles of NaOH divided by the volume. So 1.4983 into 10 raised to power minus 3 mole divided by 0.01480 liter, which is 0.101 mole per liter. This is the concentration of NaOH used. I hope you understood all of the things that I have discussed. In the next class we will move to the next chapter. Thank you so much.